should start, but I want to say a little something because there are 1, 2, 3, 4 strangers in the back because I haven't seen you. We've been here for 2 weeks every day, and this is the first time I see you. Welcome. And the theme of this workshop has been based around the persistence of water at low temperatures in the presence of ice. And the reason I have twisted Hans Agren's arm to come here is that he's one of the few local people who works on pretty much everything that we've been talking about, but in particular biomolecules and water, and he's also worked on GFP, and these gentlemen here, Yoshi Furukawa and Ido Braslavsky, are two of the world's experts on the mechanism of antifreeze glycoproteins in suppressing the growth of ice crystals, or attaching to the surface of ice crystals. And what they do, and part of what they do, is cross-link the antifreeze glycoproteins with GFPs and use fluorescence methods to look at them where they are on the surface. And we've spent a couple of days making bald speculations and false statements about how these things actually attach to the surface, and so perhaps something you're going to tell us will help us be more confused than we were otherwise.
Okay. Well, thank you very much for the introduction. And I've seen on the web that you have a wonderful conference here, a wonderful program and conference, so I apologize for not attending because I have been sick the whole week, and you can hear my voice that I'm still a bit not feeling well. Last week also I was on travel, so it has been exceedingly busy. So I hope the quality of my talk doesn't reflect that too much. I will just throw on you some results we had over the last few years when it comes to water. Of course, we've done a lot of water, single water molecules, small clusters in the old times, in spectroscopy and so on, but nowadays we are also interested in more, we say, mesoscopic properties of water. By the way, I can say that our visitors are not really visitors. We have Prakashya, who has been postdoc with us for the third year now, and Professor Shabrakalti from the University of Calcutta, who is visiting us for 2 months, I should say. We have a trilateral center with the University of Calcutta and the University of Beijing, KTH, and this is part of this program. And we have also Arul Murugan, who is postdoc, and who will assist me in this talk because he has a lot of details which I have not up to date on, so he will give actually part of my talk. I'll find out if that's okay. And we have Ella Horton, who is a high school student from Australia. She's here just this day to see how it works at the university. She's just going to decide about which program she will go when she comes. She goes back to Australia in Brisbane.
You should consider Yale.
Okay. But she will be in Australia.
No, but that's a second-rate institution. We're going to Cambridge, actually.
Okay, so let's just wave our hands. I hope I get to the GFPs, but here in the presentation here, I may get a bit scared of what I'm going to say there. Anyway, we talk about modeling in times and length scales, multi-scale modeling. That's a very popular word. And ice structures, water structures, etc., come very much nowadays into the mesoscale, or the nanoscale sometimes, which is a hard scale. We try to, so to say, attack it from below by quantum methods, which really are suitable for the atomic scale, and by classical methods from the macro scale. We don't have really, so to speak, a theory of its own in the mesoscale. So we combine theories from above and below. Quantum mechanics, molecular mechanics, for instance, is such an example. And we try to understand that. So we also do computations, and we are forced to average out degrees of freedom, coarse grain the problem to make it faster, and we lose accuracy in somehow also. So it's a control of these operations which are important. Multiscale modeling, we try to go from electrons, situations where every electron counts, situations where every atom counts, over to coarse grain. We have some kind of graining to pure continuous methods. We try to pipe data, or we try to connect the algorithms to transcend these scales in length and in time. And I can say in that connection that we are happy to have can announce coming activities in multi-scale modeling. So next November 2009, we will have an Nordita program in multi-scale modeling here at Alma Nova. And in November 2009, we will have a summer school in multi-scale modeling, which that is a November school, not really so much summer since it's in Stockholm, but we call it still summer school. So we combine these two things, so it will be a summer school and a Nordita program at the same time. And yesterday, I don't know if you were there, we had Bill Goddard from Caltech here giving a talk, and he is one of the world leaders in multi-scale modeling. And of course, I took the chance to invite him, so he will come. I mean, he gave a preliminary promise to come here next November to be one of the prime speakers in this program. Okay. So, no, this was not very good. Now I don't know. I put in something. Well, we try to see if you. Yeah, it's some kind of. Let's try to do it like this. We try to transcend the scales. In principle, we have two methods at a time: quantum methods, classical methods, and also on top of that hybrid methods. So if you look at the length scale, we might do up to, this is an old picture, I think we should transcend very much further now, up to over 10 up to 3 here. First principles, quantum calculations on each atom, where every atom, every electron is counted for. We have classical simulations going up to maybe millions of atoms, and we have an intermediate region which we can treat by hybrid methods. In the time scale, this is an old picture, not very accurate. Well, in the time scale, we are of course very much more restricted. If you do full quantum, we are only working in the femtosecond region, and hybrid we are going to picosecond. And in classical simulations, we cannot really reach milliseconds where proteins fold were completely if we do it atomistically. So we need to go further than atomistic descriptions in order to reach the full time scale for a protein. I think that's agreeable. And in some sense, of course, the time scale is harder than the length scale. So the length scales, that's a lot of development recently. Well, this is just a further vision, which has definitely not happened now, and maybe needs 10 more years to happen. We want really an exchange of real time to simulation time to go from 10 picosecond to 1 millisecond, actually a little less than 1 millisecond. If you have that exchange of gear up in time, not more than that, we can really, so to speak, control direct feedback fashion the simulations. We want to make this happen, let's say, for a system of 10 or 100,000 atoms. In that case, we could really add to our mathematics also visualization and also sensitization through our arms. We can apply sonification, haptic arms for protein interaction and docking directly in so to speak, real time with this gear. So this is something which might, so to speak, add to our feeling for what we're doing.
Just for a sense of what that goal is, what are you currently at? How long does it take to simulate in picoseconds?
Well, we are talking about the hours at least, I think.
So
if you look at an enzyme for 50,000 atoms or something like that, and 10 picoseconds is hours or maybe days.
And that sort of several orders of magnitude
yes.
in increased efficiency can be accomplished.
Efficiency,
or
we
hardware?
need to go coarse graining. We cannot keep it atomistic. We have to coarse grain the models for sure, and huge computer development as well in order to do this. But this would be a new, new paradigm. Okay, so far when we do quantum calculations, we cannot do the full thing. We just have to consider what is the most active part, which is the most important part. This is a protein which is, well, I guess you know this one. This is also considered here at School of Biotechnology and Carl Hood's group. where they do enzyme catalysis. So you pick out the important active site of the enzyme that can be picked out from the crystal structure or can be pre-optimized. You pick it out and you study the reaction within just that active site. And in the first approximation, you can just treat the solvent as a dielectric and make a self-consistent coupling to the dielectric, so-called polarizable continuum models. These we worked on very much in the 80s, actually. Nowadays, one also tries to treat explicitly the solvent atomistically through molecular mechanics, and even in the time fashion by molecular dynamics. In that case, of course, we have to shrink the quantum core, and there are also other problems. So this is not, what you say, a state or automatic thing to do in a production context yet, but it's a lot of work out there on this. And we try to find the energy profiles, the transition states, and the and so on. So this is development took place already in the 80s, I would say, but it's as mature now. However, at our department, we also, this is also connected to water. We try to transcend the scale from the atomistic scale to the nanoscale, also in the quantum modeling. So we try to take the quantum modeling from the atomic domain to the nano domain, as I said, develop linear scaling techniques to beyond 10,000 atoms, and this has now really happened. We really try to obtain the fundamental properties through QM this way. Although it doesn't give the final answer, it's surely, so to speak, give a limiting behavior of quantum mechanics for these properties, which is important. So we cannot do advanced properties on such big systems, some simple properties we can do. And we can also, this way, maybe define the appropriate quantum region where the quantum description is good in, what we say, a multi-scale setup like quantum mechanics, molecular mechanics. And this is the result we had, actually this is 2 years old, so we can do it larger. So we can really do the water classes bigger and bigger and bigger. And we can just put in some systems what we want and see at least quantum mechanically how they bind. Even if this is not the full answer to the binding, it gives an indication if something binds by water or not. So this is, we do, this is just a technological slide. And the technique is based on a couple of things. One is so-called fast multiple moment evaluation of the Coulomb interaction. And this is interesting also from astrophysics point of view, because the algorithm originally was fetched from astrophysics, where they could do this for interacting bodies in the interstellar space. Just summing up the interactions in a way that you get the full scale linearly. It's the same problem with electrons. One have two major complications. One is overlap. We can have overlap between electron clouds, and therefore we also have exchange. So if you treat the exchange well, which we should also should have the exchange interaction scaling linearly. That's harder than the Coulomb interaction, but it works now, so we can do that. And if you just take a technical slide, we need to not only to scale linearly with respect to the operations, but also with respect to the storage. And that's a tougher requirement. And it's a lot of sparse matrix algebra going on in order to do calculations on the 10,000 atom scale. So this is a bit old slide, just the quantum mechanical binding of aspirin molecule. How does it bind? Well, we calculate the aspirin molecule by itself, we calculate the water by itself and the cluster, and we compare. We have to do some tricks like basis set superposition, compensation, and so on, and we can get the result where we add just water shells up to here to 14 angstroms out and see how this binding energy converges. I can first say that it's very basis set dependent, so this is a small basis set, this is a bit larger basis set, and it's of course dependent somewhat also how we choose sample the structures. So these are just 3 sampled structures from molecular dynamics. Anyway, we can see that the binding of aspirin converges very well when we go up to a shell of about 6 angstrom of molecules. This way. But it's not a free energy, so it's just a quantum mechanical damping. Okay, if you go for even larger systems, if you want to do dynamics especially, we have to go to molecular dynamics. Just we all know this, we just take classical forces, and these are quite simple, of a few simple kinds, and we have to define charges of the atoms, and mostly these charges are fixed. More sophisticated schemes include polarizable charges, but they take time, etc. So it's a trade-off. So molecular dynamics, I have just a few slides. Here's Pekka Marx. He is from our department. He investigates hemicellulose, how cellulose is produced in wood. It's through this enzyme. We have an active site here, 3 tryptophan units keeping this cellulose. And these active units then should cut the cellulose. It goes away. Another comes in, it feeds in and cuts away. This is the way wood grows, actually. But it's a bit of a problem. In this time scale, we don't really see this. So we don't know really what happens in the long time scale because of the limitation that we have to run. We can only run maybe 100 nanoseconds or so, 10 nanoseconds. I don't know exactly limit here.
And presumably this is sitting in water.
This is sitting in water. That's next slide. If we put it in water, it looks like this. So it's taken away because we don't see so much.
Yeah.
But the water is very, very important, of course.
And how do you deal with the potential for water?
I don't know exactly which potential, but there are a number of water potentials, of course.
But is it a point charge model, or?
Yeah, this is fully classical molecular dynamics, so it's a prescribed force fields and prescribed charges and everything here. And of course, it's dependent on that choice. So no talk about that. This is another one which borrowed from Erik Lindahl at Stockholm University. He studies voltage-gated ion channels through molecular dynamics. And you can see that he puts, this is a membrane, this is a membrane channel, so he puts water on top and back. I don't know really
how much of that is molecular mechanics and how much is quantum mechanics?
Nothing is quantum mechanics.
Okay.
It's fully okay, so really, in order to get the answers, some answers we need to go multi-scale. We can improve the force fields, the charges, by doing pre-screening by ab initio, by ab initio MD. We can get better force field maybe than the ones which are tabulated. We can also use the atomistic molecular dynamics to go one step further for coarse graining. We can really take away, like you just mentioned this, we can take away the water completely by having mediated water potentials. And then we can increase the simulation times by orders of magnitude. This is something which Stockholm University colleagues, Laxonen and Lubachev, have worked on for some 10 years. They do this through the so-called inverse Monte Carlo scheme. They do molecular dynamics calculations, get the radial distribution functions. From that, they derive a discretized Hamiltonian or potential for the various atom-atom interactions. From that, then they do dissipative dynamics without the water, and you can see the result of the distribution functions you then get with the original distribution functions, and they get them quite much the same. So now they can just take, in this case, sodium chloride, and do this sodium chloride interactions without the water explicitly.
That is, so you modify the Hamiltonian.
Yeah. Yeah, they have used, assume a discretized Hamiltonian and fit that to the distribution functions which they have. So it's going backwards. And here, they instead of considering this DNA with the charges around and water, they can then consider the DNA with just the charges or the ions around from that, and then increase the simulation time considerably. So this is one example of coarse-grained modeling, but there are many examples, and of course it's not trivial, and there are many problems with entropy and so on, but and how to divide up and conquer and so on. But I'm not an expert, so I leave it. We talk about multi-scale modeling. There is also multi-physics modeling, of course, where we combine quantum mechanics with other physical models in order to treat also water clusters, for instance. Mostly, when we talk multi-scale, we talk about the combination of quantum mechanics, molecular mechanics, or classical dynamics. So this is the combination.
In the second line, the quantum mechanics and dielectric theory.
Yeah, actually, I had an example of that. The polarizable continuum model is an example of that, where you use dialectric theory to derive the self-consistent reaction field from the quantum core out in the dialectric going back, so to speak. This is an example of this combination.
So you can, for example, test the breakdown of Clausius Mozarti in water,
Yeah.
for example.
Yeah. So we have done calculations like that. And we combine quantum mechanics and molecular mechanics. Well, I think the argument could not be repeated. It's obvious we cannot treat the big quantum part in time, at least. For big systems, we have to go to a more expedient formulation of that. Yeah, I think I don't have to. So now this is PowerPoint coming up here again. So this is exaggerated. We have a molecular mechanics part, a quantum part, and an interface region. It should be shrink very much to be realistic. Anyway, it's of course a problem. How do you define the quantum part? Should you label the atoms and make them quantum wherever they go out here? That's probably very difficult in some cases. Or should you define the volume to be quantum? Although some unimportant, so to speak, outer parts of the system penetrates in. And how do you treat the interface? How do you connect the broken bonds and so reconnect them? And how do you make the appropriate potential? So really it's a lot of work, but maybe not any consensus exactly how to do this. This is a, let's see if we can, this is a small calculation using a QMMM we had. We used one or a couple of shells, water shells around the copper ion, quantum mechanical and molecular mechanics. So this is using the so-called Carr-Parnello method, which is sort of a quasi-quantum method for the quantum part, but it's also coupled to molecular dynamics. So the question is here, it's an example, how do the water shells around the copper ion look? And it's been a discussion if it's 5 or 6 waters around the copper ion. So this has been a long discussion for many, many years. 5 and 6, it's academic, but it's a nice test. What we do here, we see, first of all, if we just do these simulations, we come up with an answer that if we ignore the Van-der-Waals interaction between the QM and MM, we indeed get a penta situation. And if we include, this is a penta situation, if we include this, we get more of a hexa situation, depending on how we parameterize this Van-der-Waals pattern. All over, this is what we found a key to one of the keys to the problem is to have this interaction properly accounted for. But this is just pure structure. So what we like to do is also to combine structural calculations with property calculations. Because we have experimental properties, we can calculate the property and go backwards and get the property structure relations. And one speciality we have is to do properties through the full spin Hamiltonian. We have worked a lot to implement that in operational DFT theory. We calculate basically all the hyperfine interaction parameters in EPR and NMR this way. One particularly important one is this G tensor, which parameterizes the magnetic interaction, giving rise to the Zeeman effect. So we look at that for the copper problem, copper water problem. We take trajectories from the Carr-Parnello, calculate the G tensor over these trajectories, and take the average. And we find that really that not only it's important to take the first summation square, but also to have a good description of the second summation square quantum mechanically, and we get a better result. It's just numbers to compare with, so of course there are uncertainties, but there is an indication that we should also take account of the second square. So maybe we should not look too much into the figures. We find that we should have predominantly hexa, We need to have quantum description of the second shell also, and we need to have van der Waals parameters between the molecular mechanics and the quantum mechanics part. So this was the result of this investigation. Another way we talk about QMMM here, structural QMMM, but what we did now was a full structural QMMM, but we took only the property on the quantum part. We really like to take the property on the full part, of course. Yep.
In the couple case,
Yeah.
were there no, let's say, excess measurements or something on the order formation number?
Not really these systems. I mean, you have what that I think is not very well.
It's rather uncertain numbers anyway.
Okay, so this is as an example that I don't want to go into details, but in order to do the full case, you also need to treat how the molecular mechanics part perturb your property inside the quantum mechanics part. And that is done by, we have not done it, but it's done in our program, response theory, where we include the van der Waals polarization and electrostatic interaction from outer to the inner sphere in a full perturbational manner. And that's also gives a contribution. Another way is to do it by X-rays, to check structural properties of water by X-rays. X-rays have the advantage of being localized. They map the local, not only the local conformations, but also the local electronic structure. So it's really the electronic cloud around the atom where the core hole sits, or where the core hole is excited, which is seen. That could be seen in absorption or in emission. It could be resonant or resonant. So here at Albanova, a lot of calculations have been done and a lot of collaboration with experimenters on water in particular. So this is one of the original results. Well, this is an experimental result. Gas phase, nexus. We then take the 1s electron, put in the first few unoccupied orbitals, and we get an absorptive structure. You see that in gas phase and in ice and in liquid. It's very much different. And Lars Pettersson here, and also the EU, sitting also in the next houses, they analyzed this. Some years ago, they came up with the suggestion that we have an extra feature here, which is due to the hydrogen bonded configurations of liquid water. Before showing that, we can also see that we can also get results from X-ray emission of liquid water. This is water molecule, the red, liquid water blue, and these are calculations. You can see this. They look, the broadening is not correct, but they look pretty much okay otherwise. So how to do this? Well, again, we have to sample structures, typical structures, which can be computed on in order to connect the X-ray calculation to what is actually seen. And you can see here that if we take X-ray absorption again, we see that we look at different structures like fully tetra-coordinated and then tree-coordinated with the accepting hydrogen bond bond, and here is tree-coordinated with the dominating hydrogen bond gone away. We see that this configuration gives a lot of signal at this extra peak here. So this is a signature that one really has this in water. And these are also the X-ray emission of the same thing, and it's seen that I think one looks for a while that it also supports this interpretation that there is some of this. The question is how much, and that has been debated very much. I don't think we can say that it really breaks a common picture of liquid water, but it surely gives a nice verification that there are some presence of a broken water in the liquid case.
Can you calculate the density difference between these two types of water?
Density difference?
Yeah.
Well, that's through the molecular dynamics. I don't know how accurate that would be. Do you know the density difference? The densities?
I mean, because there's a so-called high density, low density water, and if this is the origin of that, and you said at the last phrase that we can't say how much of this type of water exists,
No, I mean,
I'm
from
comparing
the spectra here, we cannot really say how much. I think this is not, this is beyond the precision of the model. We should also say, yeah, because of different reasons. But what you say is to get it directly from the underlying dynamics, molecular dynamics. Surely the density is there, so there's some result. I cannot say how well that is, though.
I'm preparing myself because this afternoon we're going to hear from Lars Pettersson, who is probably going to tell us something
So
very.
will you repeat this?
He will be very definitive about these things apparently. So I'm just trying to educate myself.
No, I say my expertise is in the spectral interpretation, and beyond here you cannot say anything because you have what do you say, collective excitations, outionization. You have a different type of normalization of the spectrum which you can't do from a discrete recalculation. So there's no way one can use, I think, this way to derive anything. This is a discrete peak, which is part of the linearized spectrum, and that is more definitive proof that something is there. But you know, you have only one peak in a big bump. This big bump is not very useful. We just have this one, so it's too little. So it's peak information to give any. That's my view. It's also from X-ray emission, which is more definitive here. You can see that if you take the linear structures of water from X-ray emission, there's no way they fit into the spectrum. So the X-ray emission is more, what do you say, maybe it's hard to support anything, but it can disprove confirmation further. So that's done. We have done that. So you see that you don't have any larger chain or ring formations of water. You see that from X-ray emission. So this is X-ray emission again. We can just, we can twist and turn, put the molecules up and down, and we see that we change the spectra in different ways. We train ourselves a little by doing all this. We can also twist, and you can see that it looks not so big differences in these structures, but they really change the spectra quite much. I will not go into anything of this. On the other hand, methanol, methanol maybe is not interesting from the point of view of the universe, but methanol is more definite in the analysis here. But one has proposed earlier, of course, that there are ring and chain structures, and I think the X-ray spectra here supports that very much. And we can even say how big these chains and ring structures are, or probably how big they are. So this is a collaboration with Uppsala we have for a long time. They take the X-ray emission experiments. These are rings, these are chains. You can see that the peak here is due to rings. The right peak here is due to chains for sure. And the intensity between them supports the notion that there is a mix of rings and chains in liquid methanol. Although you cannot tell the proportion exactly because we don't know exactly the fluorescence yield. We have also non-radiative decay of these states, so they can also change. But presumably they don't change too much, and we can say actually that there is a mix. And we can also calculate the length. We have 3 methanol, 4, etc. in the ring configuration, 3, 4, 5 in the chain. We see that we have much improvement in this area from the lower area. So they should be maybe around the size of 8 or 9, something like that, rings or chains. And we also looked into, now it's getting quite complicated, how to mix water and methanol. And we see that methanol, water penetrates into the rings. They do it not by 1, 2 or 3 water molecules at the same time. So this is a proof of incomplete mixing at the microscopic level of water molecules bridging methanol chains or rings. And this was highlighted by Physics News today, and they say that bartenders should not worry too much, work too hard to mix alcohol and water because they cannot mix completely at the microscopic scale. And the joke is also that it's not only one molecule, they go in pairs, so you never go alone to the bar. So you have company with somebody to talk with.
There was an argument, or there was apparently a claim made by a chemist at UCL that if you shake the martini, you have a higher antioxidant concentration than if you stir the martini. And I've been
Now we're
trying
getting
this.
into details.
Yeah, this is important. I try this experiment very often. And I feel better when I shake the martini, but I think it's simply the surface area increases. You get more. You have more dissolution of the ice in the drink before you pour it in your glass.
We're in position to James Bond now, I think.
That's right. So be careful.
Yeah. Yeah. Okay, so I think if you, yeah, we have still some time. So I think I'll have to go to Arul here to talk about this with organics and water.
I need to do this.
No, but it's here.
No, but that is old.
Yeah. While you're doing that, I'll ask you: can you put fields on? Can you put a field? For example, you showed us a copper in water. And you also showed us a picture, I don't know if it was your own, of a salt ion in water.
Yeah.
Can you put the system in an electric field?
Yes, yes.
Yeah. And if have you done that?
Yes.
And what happens?
Not in this case, but
Yeah.
we've done other cases.
And how can you see that there's a larger number of water molecules than the static hydration shell involved in the motion of an ion in a field?
Well, I cannot give an answer to that. We have done that for a number of properties, calculation, including also in water systems. But how that affects the structure, I cannot answer. But field-induced polarizabilities, second harmonic generation, field-induced and so on. In such systems, we have done. More detail.
Yes. Yeah. Thank you.
And you had two figures of the way you parameterized the van der Waals part.
Yeah.
Is that just changing the coefficient in the effective part of the 1R6?
Probably, I don't know exactly what the difference are, so it's many ways you can
Thank you, Hans. Now we'll be talking about organic water and water-induced changes in organic water. First of all, I have scheduled my talk like this. I will discuss few unique properties about water, and I will discuss about organic water, which is the water molecules around the organic molecule. And I will also discuss about solvent effect on organic molecules. So water has many unique properties. It exists at least in 15 polymeric forms and even in many amorphous ice forms. It also exhibits liquid-liquid transition, and it has larger dielectric constant. So water is important for life. Without water, many biological molecules such as DNA and proteins will become inactive. And for example, here I just put two cases. This is a protein called haloalkane, halogenase. It hydrolyzes many haloalkanes using the crystal water to alcohol and halogens. Similarly, this cation protease hydrolyzes peptide using the crystal water, which is located between these two residues. So what is biological water? The water which is bound to the biological molecule, or which is around the surface of the biological molecule, is called as biological water, and it has many unique properties when compared to the bulk water. For example, it is less polar than the bulk water, and the thermodynamic properties such as freezing point is very different for this biological water, and even the rotation and translation and dynamics close to the protein surface for this water is very slow. So we will be looking into the organic water, and by organic water I just mean that the water molecules which are around the organic molecules. So I have divided my talk into two sections. In the part 1 I will be discussing about the effect of water solvent on this solid molecule, which is here usually organic molecule. So I have investigated the solute molecule effect or solvent molecule effect on the molecular geometry of solute molecule, and the dipole moment and charge distribution of the solute molecule, and then the conformation transition and conformation distribution of the solute molecule. So for each case, and in the second part, I will be discussing about the solute conformation dependent solvation structure, and then we will look the solvation structure for a small organic molecule, and we will also see that is there any orientation preference for the water molecules that are located in the solvation cell of this organic molecule. So we used techniques starting ranging from molecular dynamics to CPMD, and this time scale and length scale of the system which we want to study decide the techniques to be used. So this is the first case of here I just try to put what is the effect of this solvent molecule on the molecular geometry of the V time. You can see that in gaseous phase the molecule has a twist angle 30. The twist angle is the one which the diagonal angle between these four atoms. But in solution, when you put this solute molecule in water, the diagonal angle becomes 60 or close to 50. And in addition to that, it also exhibits a twist-like motion. So this is a really interesting thing that so much conformation or molecular change can be there due to the solvent. And this we studied with the CPMD QMMM setup. And this is the other case where the conformation distribution can be quite different when compared to the gaseous phase when you put the molecule in the water solvent. So in gaseous phase you can see that cast conformer is very less populated, and this is the population of tons conformer in gaseous phase. But when you put it in water solvent, the conformation distribution shifts towards the cast conformer. This is because this in cast form it has zero dipole moment, but in this in trans form it has zero dipole moment, and in cast form it has 3.54 d by dipole moment. So the cis conformer is stabilized due to dipole-dipole interaction with the solvent molecules. So here I will look into the dipole moment of this butane molecule in gaseous phase and in water solvent. So you can say that this is a gaseous phase dipole moment which is 6.55, and it can go up to 12.9 or something in water solvent. So it's a highly very big shift in the dipole moment. So I will just conclude this chapter by saying that water solvent affects the molecular geometry significantly, and the dipole moment charge distribution can be very different, and even the conformation distribution and conformation tension is highly affected by the water solvent. So in the part 2 I will be discussing about the solute conformation dependent solvation layer of these organic molecules. This conformation of the solute molecule plays important role in the structure of the hydrogen layer. This particular aspect is very less discussed in the literature because this conformation transition are very rare events, and so it's very difficult to explore different possible conformation states. So as a case study I have studied this adenosine and another organic molecule called PMA. This is called adenosine. This adenosine can exist in anti and syn conformer in water. These two forms differ to each other by this diagonal angle. This formed with this quadrant 1, 2, 3, 4. This is the anti conformation, and in syn conformation, this diagonal angle is 180. So the interesting thing is the hydrogen layer or first solvation cell for this adenosine in anti form has 5 water molecules, but in syn form it has only 4 water molecules. The reason is that the CH2OH in syn form bonds to this nitrogen and forms intermolecular hydrogen bonding. So no longer this CH2OH group is available for further intermolecular hydrogen bonding. So in this slide we will discuss about solute-solvent interaction, nature of solute-solvent interaction. It can be either site-specific or globular in nature. The site-specific solute-solvent interaction means that the solute and solvent molecules interact with each other through the specific sites of the solute molecules. But in globular in nature it is not so. So we find that in adenosine in water the solute-solvent interaction is site-specific, and in chloroform solvent it is globular in nature. So this is the other molecule which we have studied in water. This is the IUPAC name for this molecule which I will not read. So this is in literature it is called as a molecular chameleon. The reason is that depending upon the solvents, it can change the conformation. For example, in polar aprotic solvents, it exists in both open and closed conformation, but in non-polar solvent like chloroform, it is existing in this open form. So this is the angular distribution function, which clearly shows that there are three possible conformations for this molecule in water, and the two forms are open and one is closed. And this one is highly populated, and the next highly populated is this conformer. So here we have the G of R. The interesting thing is the conformation 3 is solvated with less solvent molecule, which you can see from the lowering of the peak position. This is because the conformation 3 has less molecular volume, so it can adapt to only very few solvent molecules around it. And another interesting thing is this n center of mass radial distribution function, which shows that for conformation 1 and 2, the nitrogen is available for bonding with the water, but in case of conformation 3, it is not so. So the first peak is totally missing in the conformation 3. So now we will have a careful look on the solvation cell structure for the organic molecule called COP, and that molecule structure is here. So this shows that there is we see a small peak below 4, and then second solvation cell appears up here, and then third solvation cell ends here. So we'll see how the number of solvent molecules in different solvation cell varies. This is the average number of solvent molecules in different solvation cell. In first cell it is 1.2, in the sense it fluctuates between 0 to 5. So in this slide I want to raise a question whether is there any orientation correlation for these water molecules in different solvation cells. So here RAG is the distance vector between the organic molecule and the water center of mass, and theta is the angle between the distance vector and the solvent dipole vector. So it clearly shows that there is a preference for the orientation where this distance vector and the solvent dipole vector are perpendicular to each other, and this orientation preference is there even up to the third solvation cell, and we want to see where it exactly decays. For example, so for the water molecules located between 12 and 15 angstrom of the radial distribution function, you can see here between 12 and 15 angstrom the density is 1, so it is like a bulk water. So we want to see whether for the bulk water how this orientation preference is, and you can see that it is just a straight line around 0.5, which suggests that there is no orientation preference for the water molecules located at a distance between 12 and 15. And like it's a difficult question to answer how to define the hydrogen name for organics. Like either you can use center of mass RDF, or you can use solute atom and the solvent center of mass RDF. And we find that, okay, and this is how it looks for a molecule butane, and this is the molecule. So which is better for this molecule? You can see that this solute atom and the center of mass RDF starts at lower R, and this is the first solvation cell for the center of mass RDF, and this is the first solvation cell for the center of, from the solute atom and the solvent center of mass RDF. So we see that this is going to give a better description for the solvation cell when we discuss about the non-globular molecules. So we are trying to calculate some properties using this first solvation cell and the earlier one, and we try to see which gives better results so that we can adopt this procedure. So I want to conclude this chapter again by saying that the solute conformation strongly decides the number of water molecules in the first solvation cell, and the solute solvent interaction can be either site specific or globular in nature, but usually in water it is site specific. And there is orientation preference for the water molecules exists even up to third solvation cell, and in case of this molecule the orientation preference disappears after 12 angstrom. And solute atom and solvent center of mass RDF can be a better way to describe the solvation cell for non-globular molecules. Yeah, so that's all I want to thank Mr. Collins and all these people.
Thank you. I have a few that slow. Very quickly. Can I just
Yeah,
ask a few
your problem
questions?
is the time was limited.
I understand.
Yeah.
Yeah. None of the molecules that you show I recognize. If it doesn't have one single ion, it's too confusing for me. But I ask, you show examples where you have different conformations.
Yeah.
Did you? But I didn't get a sense of what happened. What happens if you have n such molecules in the solvent? What's the distribution of conformations in thermodynamic equilibrium? Which one is more likely? And so that's the first question.
Yeah, I will answer that.
Okay.
See, whether you take one solid molecule or many solid molecule, I think the conformation distribution should be the same at a particular temperature.
Okay, in the
So,
dilute,
in a particular solvent, yes.
as long as dilute.
Yeah.
Okay.
Yes.
So what does it then say about the standard colligative properties in the dilute limit if you have, say, 3, or what you showed, or n different conformations of a complex solute? How do I understand the colligative properties in the dilute limit?
It's like different conformation will be weighted by the Boltzmann weightage at a particular temperature. So any property should be weighted over all these possible conformation states.
I mean, have you tested that?
Yeah, we are trying to calculate some spectra for adenosine for this syn and antiform, and then we want to calculate compare with the experimental one, so that which is a better way of how to get the exact spectra. So we are trying to do that. Yes.
So a different question is, you said that this bio water,
Yeah.
It has these different properties,
Yes.
which, given what we've been arguing about for a couple of days, seems to be rather important. So we would like to understand, for example, how a antifreeze protein decides what surface of ice to attack. It attaches to a certain orientation rather than another orientation, and the fact that you find in your systems that locally this bio water has different properties and different conformation seems rather important. Have you looked at the effects of that when you bring such a molecule towards the surface of something, or is it always just in the bulk?
It is always in the bulk which I have studied. So
And the water and the potentials for water you use in all these?
it is tip 3p.
So, and you can really think with tip 3p that you understand that the dielectric properties of the water, of the bio water, are different than bulk.
No, actually here we are looking at the orientation difference, and even we are trying to look into this, how this water molecule is different, or how it compares to the biological water. So we are trying to do some ab initio calculations. Like we take the configurations from the MD, and then we try to this will be frozen. The coordinates for this frozen, and we release that and do the ab initio electron calculation and see what is the dipole moment for that. Is less polar like biological water. So we have some preliminary results where we say yes, it's true.
Thanks, Adam.
The different in this diagram where you had theta 1 versus theta 3, I think it was, you had 3 separate clouds.
Yeah,
Should
exactly.
I think
Yes.
of these are thermal fluctuations, simply the width of the cloud, or is there some more to that?
You're talking about this slide.
Right.
This one.
Yeah.
Okay. See this theta 1 and theta 3. They say that how these different flame rings are oriented to each other. So there are 3 rings you can see, 1 and 2 and 3.
So
for each conformer, this angle is it takes a particular value. So
yes. Oh, I see. So they're not really not thermal fluctuations at all. All different realizations. So what about your question about the antifreeze protein? Do you think Can be answered, or?
No, no. I mean, but it's certainly partly news to me about. I mean, it's a quantitative question about how the properties of the biowater, how much they change. Because we were making a model yesterday. So these antifreeze proteins, you can use experimental observations, which these silent gentlemen have made to estimate the surface density. So the surface density is about 20 nanometers, so it's spacing. So one question is why? Well, why 20? These are tens of kilodalton biomolecules, and it may be due to the fact that when one side is hydrophilic, the side away from the ice, and we're trying to understand what sets the spacing of these on the surface, and yeah, and so this isn't.
We should have brought Pekka Mark here also. He is actually looking into these problems for the protein simulations of this the action of different kinds of protein surroundings. Unfortunately, he couldn't come today.
I mean, it turns out, as often happens, is the spacing is commensurate with a model which is somewhat reasonable but inconsistent in terms of the behavior of how it influences the surface of the ice. I happen to not like that model at all, but the idea that the surface water, the biowater, what you're calling biowater, is rather different is appealing, because it means that we could, for example, change the background solute concentration, and that would have a specific effect. For example, make a Debye layer which is different around the biomolecule, the hydrophilic side of it, than it would be otherwise. And so that would make the protein-protein interaction on the surface have some length scale.
There is some work on the influence of salt on antifreeze protein. I should look into that.
I mean, so far.
That influence is huge. If you have salt ions presence, that would change the whole thing, of course, very much. The problem is, where are these ions?
Right. This is the problem. Partly, I mean, these antifreeze proteins are made in a salt solution, and of course that is in part mimicking what happens in the actual organism. You know, they exist in fishes and worms and bugs and so forth, and not in us. So the absolutely the salt is important. The question is how, but this kind of simulation showing that the water properties are different is essential to understand how the ions actually interact with the hydrophilic side of the protein. And all of this discussion is simply made up in the last 24 hours.
What is actually the range of different antifreeze proteins? I mean, how many different ones are there?
There are 8 naturally occurring antifreeze glycoproteins, which have about an order of magnitude range in molecular weight. For example, Yoshi showed experiments that they have a dramatic effect on the shape of how the ice grows. Striking effect. So they seem to, in some cases, attack one orientation of the ice surface rather than the other, and they attack the right orientation, and somehow they know where to go, and that's what we're trying to understand. But the experiments that Yoshi showed had a mixture of 3 types of AFP, so-called 4, 5, and 6. In different percentages, and so his experiments have tried to look at the different conformation of these on the surface of the ice, whereas other people study AFPs, which are manufactured, so to speak, by biochemists, and which are specific, so you just have one. But in the naturally occurring organisms, they have like the spruce budworm that I showed yesterday has one type.
I'm not sure what you're asking about. How many you have? How many known in nature, or how if they
Yeah,
work
but he
together?
basically answered this. I mean, in the sense that there's a order of magnitude and range of mean molecular weight, for example. Actually, another question. I mean, one of the that's now really digressing from the original topic, of course, but towards astrobiology. I mean, one of the one can almost call it the success of astrobiology, but it's not really quite that way. Is of course when the extremophiles were discovered. That can work at temperatures up to 100 centigrade. They became, of course, of extreme industrial value for doing PCR reactions back then. So that really became a huge industry. Is there anything like that for antifreeze proteins, perhaps?
For sure.
Yeah?
Yeah, so I made the flip statement in my colloquium yesterday about Unilever using them in ice cream.
Yes.
And they don't call them antifreeze proteins because people don't want to think they're drinking or eating antifreeze. But it's so the idea is that there's a thermal hysteresis for the antifreeze protein, so that the freezing temperature and the melting temperature are not the same. So that they actually inhibit refreezing as they should. And so instead of adding extra fat to the ice cream, you keep the fat low and you put in this antifreeze protein, but you don't call it that. And so that's one big.
So it's already in the market. It's you can find them in ice cream. This is one thing. There's in cryopreservation. People try to use it, not with use success so far, but I think this is an application that people look into, because animals do protect themselves with these proteins, not only in mild conditions, also in harsh conditions. But and there's a little bit bigger class from antifreeze protein. This is ice binding proteins, which include antifreeze protein, but also ice nucleating proteins, which are very similar in some aspects, but actually promote nucleation instead of inhibit. And you have animals like frogs, which will just completely freeze and then thaw and keep going. And so this is the perfect cryopreservation, right? They're just alive.
I have a relative like that.
Yeah, and then it's another business.
And if you want to get rid of these budworms, so we can't do it by waiting for the winter, apparently.
Yeah.
So you have to do something else then. What do you do? Is that if you want to get rid of these budworms, spruce budworms, how do you do that? If they protect themselves
So not by
waiting in the
freezing.
winter.
You want to change their bio-water. You
Yeah.
have to inject each one of them individually.
Yeah.
Well, I don't know how you get rid of them. I mean, if you turn it on its head, so the other application is, like you said, cryopreservation. One is the dual of that, cryo-killing, which is a big aspect of cancer therapy. So people would like to freeze tumors.
Yes.
And so you would like to be able to understand the most efficient way to do that without damaging the non-cancerous tissue.
Yes.
And,
right.
And so there are a fair number of investigations of that, and without adding anything to the tumor, you can use thermomolecular pressure and freeze very slowly, but of course that's not very good to tell the patient you'll be here for 6 weeks with this needle in your side. That would have the most damage. So one is to do what Ido shows, that you can actually take a crystal of ice above its melting temperature by coating it with this protein. So it's like superheated ice, and it goes quite high above its melting temperature and vanishes quickly. The other side of that is if you take the same crystal and you supercool it, its growth is suppressed until you get to beyond a threshold when it explosively grows. If you could control that process, you could kill tumors efficiently. So you inject this protein. Do you want to volunteer? You can volunteer. And you're standing there. And you can inject the protein into the tumor and then supercool it using liquid nitrogen, and then possibly, if you could control the freezing, you could destroy the tissue. It's also just an issue of preserving food when it's frozen. How should you do that to have the best outcome? So but Ido said that people in agriculture have tried to use it for suppressing crop damage or something.
And this is a general thought, and it's to try to put genes, to transfer gene into a.
Yeah, thanks.
Thank you very much.
Well, I'll just break it up, but thank you very much for coming, and now at the very least, some of us know the relevance of what some of us know and what some of us don't know. So, thank you. Appreciate it.